Okay, so this is the second of two lessons on related rates. In this unit, there will be another lesson down the road in a different unit. And as I said in the last lesson, we're going to do another problem that involves Pythagorean Theorem, but there's nothing really different about this one than the other ones that we did. It's just another one for practice, and then we're going to introduce another strategy that is a bit different. Okay, so let's get into it. Remember the strategies from the last lesson. I'll let you go back over those, but hopefully you've been doing some practice before you watch this video, and then maybe some of the tips along the way will sink in a bit better. But remember those strategies, and be mindful that application problems like these can be hard to get started, and so those were supposed to be, the advice given was supposed to be some tips on just things that you can do to start working. Even if you're not sure how the whole problem is going to unfold, those are always things that you can do. Car A is traveling west at 60 kilometers per hour. Car B is traveling north at 50 kilometers per hour. Both are headed towards the intersection of the two roads. So we have car A traveling west. Again, really important to put these arrows on the diagrams to show direction. Car B is traveling north. Both are headed towards the intersection. So that's how I know that they are going towards the intersection, because obviously you could be heading north and have already passed through the intersection. Okay. At what rate, and again, I mentioned this last time, it's really important that this diagram gets drawn properly and is labeled properly. It can be hard to wrap your head around exactly what's happening, and you may have to draw the diagram a couple times. I definitely see people, drawing a triangle, realizing it's wrong, and then scratching it out and starting again. Like if you drew a triangle like that, that would not work for this question, right? You don't have to get the east-west part necessarily correct, but you have to have the arrows pointing towards the intersection, basically, in this case. At what rate are the cars approaching each other when car A is 0.5 and car B is 1.2? So car A, again, was this one. Car B, I'm just going to use A and B, and I'm going to use L for this, and obviously this is a right angle. Okay, and my diagram is drawn. And then I'm going to start listing my givens. Car A is 0.5 kilometers. And it is car A is traveling 60 kilometers per hour. Again, per hour means everything is compared to time, so I'm going to be taking the derivative with respect to time. And here's what this diagram really helps us understand. When I list this rate, I have to know that it's negative. One easy way to think about whether something should be positive or negative is if it's a length that's getting bigger or smaller. Okay, and this one's getting smaller because it's going towards the intersection. So the length from where car A is, which is over there, the length from that to the intersection is getting smaller. So that means the rate has to be negative. And then B is 1.2 kilometers. So my diagram is a little backwards in terms of its scaling, but that's okay. And car B is also negative, has a negative rate. The distance is getting smaller. And I mentioned this in the last lesson. It did come up a couple times, I think, that this is a common mistake, and it's an easy thing to miss, and you just have to get used to actively thinking about whether a rate should be positive or negative. And you can do that, as I said, by thinking about whether that length is getting bigger or smaller. In some cases, it's going to say the side length is increasing or the width is decreasing. And so then, again, you'd have to make it negative if it said it's decreasing, but it might be a bit more straightforward. In these, it tends to be these cases, like these car questions, where we miss the fact that the rates should be negative. Okay, so find. It says at what rate are the cars approaching each other? That's L, so find dl by dt. Okay. And this is Pythagorean Theorem. Take the derivative. Everything is changing. We did a ladder question where something wasn't changing. That's something you do want to think about, but all three of these lengths are changing. Oops. Okay, again, divide through by 2, and all the 2's are gone, and start subbing in. Although, what do we realize after we've done this? This is something I talked a lot about, so we'll get rid of the 2's, and then I've got 1, 2, 3, 4, 5, 6 givens. 6 variables. One of them is what I'm looking for, so I should have 5 that I know the value of, but I don't. I only have 4. Okay, and so this is when you realize, oh, we need the value of L. And in some cases, and the more you do this, you'll know when this is going to happen and when it's not. In Pythagorean theorem questions, basically, it almost always happens where you need this value, but there are questions where you don't. We talked about one of those in the last lesson. But, when you get there and you realize you need it, then you just have to go find it. So we find that by using Pythagorean theorem. L is the square root of a squared plus b squared, which works out to exactly 1.3. Putting that into your calculator. Kilometers. Oops, got rid of the 2's. That should probably be a small a, just to be careful there. Okay, and then we're just doing all of this on the calculator. The right side here works out to -90. Divide by 1.3, and we get approximately 69.2. Therefore, negative 69.2. So again, really important that we do a therefore statement in a case like this to explain what the negative is. Even though I think I said it in every example we did in the first lesson, and I'll probably say it in every example in this one. People still don't do it. They say therefore the rate is negative 69.2 or something like that. And that's not going to be good enough. Okay, you're going to lose mark for that. So therefore, the cars are approaching each other. So the word approaching implies their distance is decreasing. The distance between them is decreasing. You could also say the distance between the cars is decreasing. It's fine to always just use the word increasing or decreasing if you want to be safe. But, this is a clear way of and a fine way of saying that the distance between them is decreasing. If they're approaching each other, then that's what's happening. They're approaching each other. And so I drop the negative, and your answer will always be written as a positive, but interpreted, whether it's increasing or decreasing. All right. So this is going to be a bit of a new type. There's going to be a bit of a twist to this one, or something different about this one, but we'll get to that momentarily. The more of these examples you do, the more of the work that you get through, the more you're going to get used to the way these questions work. If you were seeing a question like this for the first time on a test, I would imagine it might not be clear exactly what it's saying. But once you've done one and sort of thought about it, then it makes sense. Gravel is being transported by a conveyor belt at a rate of 2 pi meters cubed per minute to a point where it falls and forms a concise pile. And so think about what would happen if you were just pouring sand out of a cup onto a floor. It would form a cone, right? As it would form a pile, and that pile would be in the shape of a cone. So that's what's happening here. And where the base radius of the pile is always 3/4 the height of the pile. Okay. how fast is the height of the pile increasing when the height is 2 meters? And then there's another part, how fast is the height increasing when the volume is? So notice this one gives me the height and this one gives me the volume. Otherwise, they're going to be solved very similarly. But examples like this, in particular in lessons, highlight the difference between, when you're given one value versus when you're given another value. When we're given the volume, there's going to be an extra step. And this is very similar to an example we did in the first lesson. So we've already seen it, but we'll see it again. And hopefully, it's to me, it's pointing out something nice that we just need to be aware of, kind of thing. Okay, so this is one of those cases. Now I'm going to label this as H and this is R. This is one of those cases where the diagram doesn't do very much. You could label your givens on the diagram if you chose to. That's still not, there's not going to be a lot of them in this case, but you could. I still like to do it because it's sort of a way of defining variables. And although, again, when you're using a formula, a measurement formula, you don't really have to define those variables. You can just use that formula. But I don't know. It's still a visual thing for me, and so it allows me to sort of make sure that I'm on the right track and make sure that I'm thinking about the problem in the right way. So I do like to do diagrams even in a case like this where it's not super necessary. And it just kind of gets you started on the question. It's always a good place to start, is by drawing out the diagram. Okay, so I'm going to list some givens. One of the things that we're given, notice that this is meters cubed per minute. So that's a volume and that's a rate. So dV by dt is 2 pi meters cubed per minute. And that's the only one I'm given because the next given is in part A. Now, the other thing I'm given is this. I'm going to start the question and come back to that because that thing has to do, this piece of information has to do with how this question is different. But I'm going to try to demonstrate why it's different before we come back and use that piece of information. So for part A, we are finding dH by dt when h is 2 meters. Okay, so there's my other given. That's only a given for part A. It won't be true for part B. And I'm finding, but in both cases, I'm finding the rate of change of the height of the pile. How fast is the height of the pile increasing? How fast is the height increasing, right? Okay, so we're going to use formula for volume of a cone, and that is volume equals 1/3 pi r squared h. Now, what would be the next step? It would be to take the derivative and start subbing stuff in. First of all, I don't have r, but I could find it because I know the relationship between h and r, and I know h. But something that may not jump out at you about this question is what would happen when we were taking the derivative? What kind of derivative question is this? I want you to think about that for a moment. So you'll have to notice that this would be product rule. And so the derivative would be a little bit trickier, but it wouldn't be too hard. But it would be product rule. But when I do this and I take the derivative of r, I'm going to get a dr by dt. Well, what is dr by dt? Right? We don't have it. We don't know it. Is there a way to find it? In some cases, there might be. And so you could do this question that way, but it would be harder. It would take more steps, and the derivative would be harder. You'd have to make sure you recognize it as product rule and do that properly. Again, it's not super hard. You just have to notice it and be careful when you're doing that. In some cases, you kind of can't. Like or at least it's harder to do, a lot harder to do. So, instead of doing that, what we're going to do is we are going to do a substitution. Okay, and I'm going to use this piece of information. The radius is always 3/4 of the height of the pile. And so before I take the derivative, I can sub in for r. making sure I'm subbing in correctly, and then I'm going to simplify first. And now I only have one variable on the right side, and it's no longer product rule, and I'll only have dH by dt. I won't have dr by dt, and it's just going to be a lot easier to solve. So this is called, we call this a substitution, okay? And often in these volume or measurement kind of questions, you can do a substitution to make the question easier. And often you'll notice when it gives you some kind of relationship like that. Okay, we're going to see another example of that in example 3 that's a little bit different, but again, it does have that kind of language in it. So you want to notice that this is a question where you can do a substitution. And then it makes a lot of sense to do that substitution, right? So now I'm going to clean this up. So I'm squaring 3/4, and one of the 3's is going to simplify with the denominator there. So this ends up being 3/16 pi, hopefully. And then h squared times h is h cubed. Hopefully you can follow that. But all I did was square 3/4 and multiply it by 1/3. You could do that on your calculator. Take the derivative. This is one of those situations, as I just said in the last example, where when I take the derivative, there's no v, right? In the last one with Pythagorean Theorem, the length was still in there. It was L times dl by dt. But in this case, the v is gone. So we don't need to know the volume. And that hints at how this part B is different. It gives me the volume, which I don't actually need directly. Okay, so that works out to 9. I'm bringing this 3 down. 9/16 pi h squared dh by dt. Now I'm going to start subbing in. So we know dv by dt, it's 2 pi. We know h, and we are looking for dH by dt. So I only have one variable left, it's dH by dt, and I'm just going to solve for that. The pi's on both sides divide out. I can divide the whole thing by pi, and those are gone. And I'm going to square the 2 to give me 4, and kind of move things to the other side, and you end up with 8/9. You can do that in 2 steps, obviously, it's totally fine. I just did it in 1. Okay, and that's that one. So it's positive, it's increasing. The question said, how fast is the height of the pile increasing? So I'm not too worried about the interpretation. Yes, on a test, you would still do a therefore statement, but we're going to move on to B. Now, the thing about B, again, and this was similar to an example we did in the last lesson, is that everything's going to work out the same. We're still doing the same substitution. All of that's the same, and we're still going to get to this line where I have the same derivative. Okay, and we're still solving for dH by dt, which means we still need the rate of change of the volume, but that's the same as it was in part A. And we still need height, and we don't have height. So that's our problem. And it doesn't, just because I'm given volume doesn't mean that's what I need. To solve this question, we're always going to need height, okay? So we're just going to use the volume to find the height, then we'll have the height, and then we sub it and solve the same way. So question B is find dH by dt when volume equals 12 pi, right? But we need h, right? Not v. So let's find h. And I'm going to use the subbed in version because why not? We've already done this work, so we don't have to show it all again. And this will allow me to solve for height more easily than having to try to figure out the relationship with r. Okay. Again, if you think about doing this without this substituted version, how would we solve for h? We would have 2 unknowns. We wouldn't know r and we wouldn't know h. So you wouldn't be able to solve for that. you would have to sub in using that relationship in order to solve for h. When I move, so the pi's again cancel on both sides, divide everything through by pi. So I multiply the 12 by 16 and divide by 3, and I get 64. And the cube root of 64 is 4. So again, this obviously was designed to work out nicely, and that's meters. And so now I have a nice height, and now we can go, and again, I've already taken the derivative, so I'm just going to use that, right? And start subbing in. And in this case, again, the pi's divide out. 4 squared is 16, which divides with that 16, and you end up with dh by dt is 2 over 9. And again, the question said increasing, so I'm not worried about interpreting that in this case. Okay, one more. This one's a little bit trickier, I would think. Okay, again, I've already got the diagram, so if you want to pause the video and draw out your diagram, I think it's not a bad idea to have a diagram for this one. A trough is 10 meters long, and its ends are in the form of inverted isosceles triangles, so this is just being careful in the instructions so that you draw the triangle properly and you're not making any assumptions. But basically, that's always going to be the case for these kinds of questions. And so the triangles are 3 meters across and have a height of 1 meter. So that's the entire triangle that it's talking about, okay? We're going to come back to that. Water is flowing in at a rate of 12 meters cubed per minute. So there, again, it's giving us the rate of change of volume. How fast is the water level rising? When the water is 50 centimeters deep. So we are finding the rate of the water level rising, and it gives us the height of the water, the depth of the water. Now, maybe I'm going to start listing some things. So we'll call this L. Okay, I'm going to call this H. I'm going to call this whole length across the top B. Okay, so that's from there to there. A trough is 10 meters long, so L is 10. And something important about L, what do you think? It is not changing. So again, the drawing out this diagram is useful because you can visualize what's happening. The size of the trough isn't changing. The amount of water in it is changing, so the height of the water is changing. But that means the length of this thing is not changing. But the base, as the water level increases, this is getting longer, right? It's getting bigger as the water level rises. The amount that it spans across this trough will get bigger, and obviously the height, the depth of the water, the height of the water is increasing as well. It's getting bigger, changing. We know that it's increasing because we can visualize it, but it's changing. Sometimes you have these questions where the water is pouring out from a hole in the bottom at some rate. So you can have these where the height of the water is decreasing. Just be aware of that. But in this case, it's pouring in, so it's going to be increasing. So it tells us the rate of change of the volume. It's 12 meters cubed per minute. And again, we're finding dH by dt, and it gives us the height, which is 50 centimeters, which is 0.5 meters. Everything else is in meters. Again, I like to write out the units because of that. Everything else is in meters, so I had to convert that into meters. So everything is in the same unit. What is the formula for volume of, this is a triangular a prism. And so volume is 1/2 length times base times height. Now, remember what I said. When you have something that's not changing, it's good to sub in for. So I can sub in for L. So that's not going to be, this is not going to be extended product rule, thankfully. That's what it would be if I didn't sub in for L. But only because L is not changing. Remember, you can only sub in when something's not changing. If it's not changing, I can sub in for it. And I can, and so then I won't have to worry about taking its derivative, right? I can simplify before I get there. But what about B? We don't know B. We know the relationship, and I'm going to talk about that in a moment. It's not maybe as obvious what the relationship is, but we know it. And but if I didn't sub in for it, again, I would have product rule, and I would have a dB by dt, and we don't know the rate of change of the base, and we're not looking for it because we're looking for dH by dt, so we'll end up with too many variables, and it'll be too difficult to solve for. So what we want to do here is we want to substitute. Now what I want you to think about is this. So I'm just going to come down and do this, and I'm probably going to scratch it out after. As the water level rises, okay, it's always going to have the same. It said that the top was 3 and the height of the whole thing was 1, right? Height of 1 and the base are 3 meters. But that same ratio will be true no matter how high the water level is. So this is what we need to know. And then we can say that the ratio of the base to the height is the base will always be 3 times the height. Okay, and this can be a useful way of writing it to make sure that we get the next step right. I'm just going to solve this for B because I want to sub in for B, and I get B equals 3H. Sometimes that's going to be fraction. This time it worked out to a whole number, but that's how you do that. So now I have this substitute. I can substitute in for B, and it's going to make everything a lot easier. Okay, but we have to sort of visualize and recognize, and now that you've seen this once, hopefully you'll be able to do it on your own next time it comes up, that as the water level rises, it's always going to have that same ratio as was given for the entire triangle. Okay. Okay, so let's do that. Subbing in. We can sub in for L, and we can sub in for B. So 1/2 times 10 is 5 times 3 is 15. So I get 15h squared. Derivative. And at this point, it's pretty simple, right? It's often with these, it's the setup that's hard. Taking these derivatives is often pretty simple and sort of the same every time. Like Pythagorean Theorem is the same every single time. That was a really easy derivative, polynomial derivative. H was 0.5. And we're looking for dH by dt. And so dH by dt works out to 12 over 15. Which is 4 over 5, which is 0.8 meters per minute in this case. Therefore, the height of the water is increasing at 0.8 or 4 over 5 meters per minute. Okay, so that was, I think, a trickier substitute. These trough questions can be a little bit tricky. You need to be able to do that so that you can sub in to make your life a lot easier. And again, we just listed out the givens. We recognize that L was not changing. That was pretty crucial because that makes the derivative a lot easier. So there are a lot of little things to these. But when, make sure you've practiced 1 or 2 of these. They definitely tend to come up on tests, or some kind of substitution question will be there. And I think sometimes recognizing substitution questions is the trickier part that students miss or that people miss. So, look for that. Look for when you get to the step where you've written out your formula, if it's got too many variables and you're going to be doing product rule, you might take some time and think about, well, maybe there's a substitution I can do to make this a lot easier. Or look for things that are given in the ratio of each other. or if it's one of these trough questions, you know, expect that it's probably going to have a substitution involved. Okay. So that was our new technique, substitution, and another Pythagorean theorem, and a lot of things to think about, whether length is increasing or decreasing, and little tips, reminders of listing out givens, looking for things that are changing or are not changing, drawing diagrams and labeling them properly, especially in terms of direction, is really useful. And hopefully that helps, and good luck with the practice.